We'll get back into the operating system design patterns discussion, which we had started last time. And remember, we covered several different approaches that were kind of unappealing. So we had simple structure, which is basically to say no structure, and MS-DOS is a great example of that. There's interesting details in the background of MS-DOS as well. If you're curious, you can go look at the history of that. We could have all ended up using another operating system called CP/M for PCs, but there were various issues there, and Bill Gates was able to capitalize on that opportunity and create MS-DOS, and now the world is the way that we know it. Layered structure, which is the THE OS, is a good example of that one. Monolithic kernels, where you look at initial versions of Unix and Linux, and modular kernels, which, again, modular kernels are monolithic, but they just allow you to dynamically load and unload portions of the kernel into memory. So they get statically linked into the kernel at runtime, and they can access anything in the kernel. The kernel can access them if they know about them. So you can't really say it's not monolithic. So modular kernels are just sort of a subset of monolithic kernels. We also talked about the separation between policy and mechanism and how important that is, because mechanism is probably not going to change very much, and it's usually grungy and low level, and you want to encapsulate it. You'll see that pretty significantly as you go through the course. But policy is something that you might want to change a lot, and it tends to be a higher level consideration. It tends to be something where changing policy can have profound impacts on performance or other aspects of the system behavior, but the mechanism is just sort of a grungy detail of how you do things. So a lot of people looking at operating systems asked a really good question, which is, what facilities do we actually have to put into the kernel? Do we have to put everything that's in a monolithic kernel in the kernel? There's a lot of stuff that you could look at and say, well, actually, no, I don't really need to put that into the kernel. So what kind of facilities would need this? Well, you think about, okay, process isolation. Clearly, I need some way of isolating processes. So that has to run in kernel mode. Context switches clearly have to run in kernel mode. Maybe a few other things that have to be in kernel mode, but if you think about it, very little actually has to be in kernel mode. So you look at these kinds of things, managing the virtual memory system or the interrupt controller, clearly setting up interrupts, being able to receive interrupts. The system call layer really should be in the kernel somehow so that I can protect applications from the kernel and vice versa. So another approach is called the microkernel approach, which is to basically put as little in the kernel as possible. Everything that doesn't need to be in the kernel is taken out of it, and it lives in a user mode application, if you will. It's a system application, but it's still outside of the kernel. It's running in user space, in user mode. Okay? And so like I say, most of the operating system is actually provided as user mode processes. So what facilities should be included in the kernel? Well, there was this guy, which we'll be talking about quite a bit today, Jochen Liedtke, and he had this minimality principle, which is stated here, and it's not complete, but it's stated here, and it's a pretty good guide. So a concept is tolerated inside the microkernel only if moving it outside the kernel, i.e. permitting competing implementations, would prevent the implementation of the system's required functionality. So things like virtual memory paging. Who gets to choose what page should be evicted? Well, that's something where having competing implementations makes a lot of sense, because sometimes under this kind of workload, I might want one kind of virtual memory pager. Under a different workload, I might want a different pager. So that makes a lot of sense to move outside of the kernel. Should I be allowed to have multiple competing implementations of context switches? That makes no sense at all. There should really only be one way of doing a context switch in the system. So that should be inside the kernel. So you can see that this was sort of his guiding principle when he was trying to think about how microkernels should be constructed. Now there's obviously another aspect of this which is not stated, which is that some things have to be inside the kernel because they can only be implemented in kernel mode. So that's another thing that should be part of the kernel, is if it can only be implemented in kernel mode. He doesn't really talk about that, but it is a critical aspect of what should be inside of the microkernel. So that sort of drives what is in microkernel. So these are the kind of things you typically see in microkernels. Process abstraction, so how do I do context switches? How do I actually manage CPU scheduling? So there's some details of that that will be in the microkernel. Interrupt handling has to be in the microkernel because the interrupt handler has to typically run at in kernel mode so that it can access the hardware. Interrupts need to be acknowledged, all of those kinds of things. Memory abstraction, so being able to do address space isolation needs to be inside the kernel. The memory separation between the kernel and user applications has to be controlled by the kernel and so forth. And then you have this other broad category of things, inter-process communication, which I abbreviate throughout this lecture as IPC. And typically you hear people call it IPC if they have been programming a lot, systems programming a lot. So inter-process communication facilities. If you have all these user mode applications implementing parts of your operating system, they have to talk. So you have some kind of IPC mechanism that allows user applications to communicate, and that's facilitated by the kernel as well. So you see basically three things that ends up being in microkernels. And so they end up being really small. Who here has heard of Minix? Anybody heard of Minix? A few of you have heard of Minix. Minix is a very well-known microkernel implementation of Unix. It was developed by Andy Tannenbaum. You, again, may or may not be familiar with the sort of very hot but now cool but still ongoing feud between Andy Tannenbaum and Linus Torvalds, because Linus said, well, you really need to develop a monolithic kernel if it's going to be a usable system, and Andy Tannenbaum was very strident that saying, you have to do it as a microkernel. There's no way you can have a stable, running, mature system if it's going to be a monolithic kernel. And of course, now history has borne out that you can definitely create very stable and reliable systems on top of monolithic kernels. And there's a few other things that have come out of the dispute over time as well that we'll actually talk about as we get into the issues with microkernels. But Minix is an example microkernel. It's 6,000 lines of code in its kernel implementation. That's really neat. I mean, you can actually, a single person could write that, and a single person could maintain that. The Linux kernel is humongous in comparison. It is huge compared to the size of a microkernel. Okay. Now, obviously, microkernels depend on a lot of other facilities that are written in user space applications, but so all told, the operating system might still be about as large. But we're talking about what actually lives in the kernel itself. Okay, so other facilities provided user mode programs, device drivers. Yay, we can have really buggy device drivers, and they won't bring down our entire system. File systems can be implemented as user mode programs. Virtual memory pagers. And when I say virtual memory pagers, what I mean is it gets to figure out what page gets evicted, it gets to figure out what page is loaded, blah, blah, blah. It's not actually managing page tables or page directories. What happens is the microkernel calls out to the pager to say, what should I do? And the pager says, well, this is what you should do. And the pager tells the microkernel, and the microkernel carries it out. So same thing with file systems. It's not like the disk controller necessarily is managed entirely by the file system code in user space, but the microkernel will defer to the file system program to figure out how to interpret the data that it's seeing and so forth. So you could really say that microkernels are on one end of the spectrum as far as separating policy and mechanism. We separate it as much as possible. We get as much out of the kernel as we possibly can. Okay, so anything that implements a system policy should be a user mode process because we want to allow multiple completing implementations. So following this minimality principle. Drivers are unusual because they do need to talk to computer hardware. So typically microkernels have to provide some way of allocating I/O ports and so forth to processes that need to use them. Because remember, the operating system kernel is still responsible for sharing the computer system resources between multiple applications in a way that's secure and fair and all of those kinds of things. So microkernel has to solve these kinds of problems. Also, you could argue that process scheduling should be outside of the kernel. The only problem is we are talking about a system that is trying to, remember, context switches are expensive. We lose about 20,000 instructions when we do a context switch. And that's a chunk of instructions. I'd like to be able to not lose that if possible. And so basically, a lot of microkernels already sort of betray the the fundamental issue with microkernels by moving process scheduling inside the kernel so that we don't actually have to context switch to user mode program and then back to the kernel just to make that decision of who should run next. So that every time you wanted to switch from process A to process B, you do a context switch into the kernel and then out of the kernel to invoke the scheduler and then back into the kernel and then back out to the next process. That would suck. So typically, it's all kept in kernel just for the performance aspect of it. Okay, so we want to use a text editor to create and save a file. The text editor is a user mode process. It's running on top of facilities provided by the microkernel. So it wants to create a file. Somebody hits Control S for the first time, or Meta X, Meta S, or whatever. It's been years since I've used Emacs. I started accidentally from time to time. But anyway, so you have to save a new file. So there's a few other user mode processes that provide these facilities. So you have a file system process and a driver process for the hard disk. And the text editor says to the file process, I need to create a file. So what it does is it actually sends an inter-process communication message, or an IPC message we say, to the file system service saying, here's the file name, here's where I'd like to be on the file system. Would you please create this file for me? So trip through the microkernel. Then the file system service says, well, yes, I'd be happy to do that, but I need to get the disk to actually have its state change, so I'll talk to the disk driver. And so it sends another IPC message to the hard disk driver to actually perform that operation. And of course, what happens is this has to occur in reverse as well. The text editor is not really able to do anything until it hears back from the file system process. And the file system process needs to wait for the hard disk to do its thing. So you have an IPC message that goes back from the driver to the file system process, and then that goes back to the text editor process. Okay? So you can see how, wow, okay, so an operation that normally in a monolithic kernel would be a pretty fast thing. Now we actually have 1, 2, 3, 4 IPC messages that are sent and received to actually perform this operation. Okay? Wow, that you know, you can probably see immediately what the problem will be with microkernels. So we communicate by message passing, like I say, an asynchronous one-way mechanism. This was sort of the way it was initially envisioned, even though here we clearly have a synchronous operation being performed. I want to create a file and save the contents to disk. So that is a synchronous operation. I really shouldn't go on until I've completed that operation. But message passing, as it was originally constructed, was an asynchronous mechanism. So I send a message to another process, and if I need to find out what happened, then I sit and wait for them to send a message back to me. Okay? But this has to be done through the kernel. So the process A invokes the kernel to send the message, and then process B asks the kernel for the message, you know, are there any messages for me? Because the file system is clearly going to be servicing a lot of other processes. So typically, this would be implemented as a set of queues. Each process would have its own queue, and when you send the process a message, it goes into that process's queue for that process to pick up the message later. And so you see you have some copying that can go on. So again, we have another issue that we sort of can run into with this approach. So the text editor sends the little create me a file message, and that gets copied into the queue for the file system. Well, that's in the kernel. And then when the file system process says, where's my messages, then the kernel has to copy the message out of the kernel memory back into the file system process. So we have a couple of copies going on. That also is slow. We would like to not do that. Now there's various other abstractions that are typically provided as well. Am I allowed to send messages to a given process? Am I allowed to send any messages at all? So the file system process clearly would say anybody can send a message to me. But you might have other processes where they're like, I really only want to receive messages from so-and-so. So again, processes get to control the kinds of things that they allow. Now, this copying issue. How might we solve this copying issue? Anybody have any ideas how we might solve this copying issue? We have all the tools to know how to make this at least a little tiny bit better just from the things that we talked about in the last half of CS24. How could we use virtual memory paging to solve this? Yeah, we could have a situation where, as an example, this is a great idea. So the text editor copies its message into the microkernel, and instead of the file system process receiving a copy from the kernel could just map that page into the file system process. So now the file system process magically sees it appear, but now we've cut it down to one copy. That's one option. There's various constraints that you could have. If we allow a sending process to write to the message that it has just sent without affecting the receiver, what the receiver sees, then we have an interesting constraint, an issue that we have to solve. So that's kind of what makes these systems hard. You basically always end up having to perform about one copy at a minimum when you pass a message to another process. Okay? There's some ways of even working around that, but it tends to be that you have a minimum of one copy that you perform when you pass messages. Okay. All right, any other questions, comments about this? So it's an interesting approach. You can see that the benefit is pretty obvious. So there's actually a couple of benefits, which I really only talk about this one, is that it is an astonishingly reliable system. The other aspect of it that's a big benefit is that you are forced to design everything modularly, and any effort you spend up front trying to design systems well is a huge boon. It's a huge benefit to spend time up front designing. So this encourages that as well. If a system service crashes, this is what's so cool about it. Just restart it. The whole system is fine. It's like, oh, my file system crashed. That's lame, but I'll just restart it. So that's nice. The printer driver crashed. I mean, the reason why I keep mentioning printer drivers is because printer drivers were like one of the things that would always cause Windows to crash before it actually got preemption and blah, blah, blah. So, buggy printer drivers from some third party, and it's got a bug in it, and the system just falls over because of it. So if you have a system service that crashes on a microkernel architecture, fine, just restart it. Now, of course, just because you can restart a service does not mean that you don't end up having sadness. Because, you may have that the file system still gets corrupted if the file system is not implemented very effectively. Okay? Or like I say here, you have a network service, and it has connections to some remote clients, and the network service falls over. Well, you still will drop those connections, or you'll still drop state that was being communicated. So you still have situations like that need to be designed around carefully. It's not like it's just a perfect world without any more thought. So the solution is the same as it's always been. And if you want a really good book about this kind of thing, then I would get Jim Gray's Transaction Processing. I'll put that on the CS124 bookshelf so that you can track it down if you want. But Jim Gray had a really astonishing, brilliant insight, which is that software fails and hardware fails. So why don't we design systems so that they can be transacted? And transactions are not just a database thing. In his world, everything was transacted so that anything could fail and it wasn't a fatal situation. Okay? But like I say here, this is not included in a microkernel. This might be a service, or it might be an aspect of a service to make sure that it's more resilient to these kinds of situations, which do inevitably occur. Okay? So that's a benefit. Another benefit, let me see. Yeah, so this is wild. I have this inter-process communication facility, and processes communicate with each other to provide services for the operating system. There's no reason why I can't put them on multiple cores now. They just talk. Or I have multiple servers in a rack, and they talk. So you can actually have one operating system running across n computers with different services provided on different machines, and they all just do their inter-process communication over a network. That's pretty powerful. And you can even implement that non-local IPC facility with user mode services, because now you have network IPC. Well, that sounds like a really great user space application you could provide. It knows how to talk to the network. It knows how to receive messages that are then forwarded onto another process on another machine. So you can see that this approach is very extensible to multiple machines. If I want to start running a system on multiple machines or multiple cores, it's very easy to do that. And like I say here, this made microkernels extremely interesting. In fact, again, has anybody heard of GNU Hurd? H-U-R-D. A few of you have. So that is a multi-computer, multi-server, microkernel architecture. It's designed to be able to run on multiple machines as a single computer, which is really interesting. You know, and I suppose that as networks get faster and faster, we'll be able to implement this kind of thing relatively easy. Of course, the major drawback, which should be obvious at this point, is the performance issue. That you have this problem that all of this communication and all of this message passing and the attendant context switches, the attendant kernel traps to receive messages or send messages, it becomes really expensive. So like I say, your message passing is asynchronous. So the text editor has to trap into the kernel. And then it gets blocked, so we have a context switch away from it to something else. And so it stores, like it says here, the microkernel stores the message in the file system queue. The file system also has to trap into the kernel to receive its message. So one message pass, 2 kernel traps, and 1 context switch at least. Probably more. Most of the time we have interactions between applications and services, or services and other services, is synchronous. Why are we trying to use an asynchronous model to solve a problem that is usually synchronous? Like I say, process A can't progress until process B responds. Nonetheless, process A sends message, process B receives message. That's 2 kernel traps. Process B sends message, process A receives message. 2 more kernel traps. It just adds up. It's kind of ridiculous. So, and then of course you have all the copying issues that also occur here. Now we're going to talk about a specific example, which is one of the most widely discussed examples. It's CMU Mach. Mach actually started out being called Mach, but there was an Italian graduate student on the team who could not pronounce Mach accurately, so he kept calling it Mach, and which is a pretty Italian thing to do. And the guy running the project loved the name, so he went ahead and decided to call it Mach. So it's not that it's blazingly fast; it's kind of the opposite. So, but anyway, it was a CMU project from '85 through '94. Very sort of impactful project. I've mentioned it before. OS 10 runs on a Mach kernel, or a variant of a Mach kernel, so you know it lives on. It's very, very widely spread at this point. So it was implemented on top of BSD Unix. It had a great approach to the problem. We'll start out adding IPC extensions, so inter-process communication extensions, to the BSD kernel, so that we can actually continue booting this operating system and using it. Great idea. After it was finished, then they started migrating facilities out of the kernel and out into user space. And so finally at Mach 3, that's when they finally had a microkernel architecture. And of course, this was exciting because of all the reasons I talked about before. You know, hey, you can run this on a multi-computer system. Because if you think about it, what had occurred up to that point was you had mainframes, you had mini computers. They all ran monolithic kernels. But they were still a single core. So it was like, okay, I can understand what's going on, even though the system is monolithic. People were starting to create multi-core systems and multi-processor systems. And suddenly, taking this giant code base and migrating it into a multi-processor, truly parallel implementation, it's like, wow, that's really difficult. And it is really difficult. And so they thought, well, if we could just go ahead and build a microkernel architecture and approach the operating system development that way, maybe we can migrate to multi-core systems really easily. And so that's why Mach was like super exciting to people. But its performance was awful. So just a little bit of discussion. I don't want to get too much into this because I don't want to lose too much time. But Mach had ports. Those were basically where messages could be sent to. And so these were set up on behalf of processes in the kernel. You would have basically ports set up, and you could specify permissions, who could receive messages, who could send messages, and so forth. And they basically, you could think of them as structs. And there was some fields that were always there, and then you'd have some sort of payload that would be delivered. So you'd say, where is it going? Where to send a message back to if there's supposed to be a response, and so forth. So you basically had all of this information that could be passed. And there was one API call that would basically send messages and receive messages. If the port queue was full that you were trying to send to, well, you were blocked because there's no room for that message to be stored into its queue. Okay? So you had this one function that was used for all of these kinds of things. And this was the constraint that I was talking about. When I send a pointer, basically, to another process, what am I allowed to do to the memory that that pointer points to after the call comes back? Am I allowed to write to it? Do I have to wait until I get an acknowledgement? So this was one of the concerns that they had to solve. So like it says here, Mach tries to avoid copying message data too many times. But if I'm going to send a message and then be allowed to write to that memory after I've sent it, but before the receiver has received it, then I need to come up with some way of protecting the message itself. And so in Mach 2.5, basically, like I say here, message virtual pages were mapped into kernel space. They would be copy on write. So if the sender tries to write to a page after it was queued up to be sent, then it would just do the copy on write trick. It would make a copy of the original, and then the sender could transparently write to its message data without actually affecting the receiver. Okay? So basically you can see here you end up with 0 to 1 copies on the sending side. I get a copy if I try to modify the data, but if I don't try to modify the data, I get no copies. When the message is received, that virtual page is mapped into the receiver's address space. So that's kind of nifty. If the sender didn't modify it and the receiver receives it, then you basically have 0 copies. That's pretty slick. If the sender decides to modify it, well, then I have 1 copy. Because the kernel duplicates the page, and then the page is mapped into the receiver's address space. So that's Mach 2.5. Mach 3 kind of simplified this a little bit. Basically, like I say here, duplicating the sender's message data into the kernel. So Mach 3 went ahead and just made a copy. So maybe I'd have to go back and look at the reasons why they abandoned the Mach 2.5 approach, because it seems better, but it's clearly more complicated. So maybe they had bug issues. Yes? That's exactly correct. Yeah. So the abstraction that the Mach message API presents is that the sender creates a message in its own process address space, and then it calls Mach message and hands over a pointer to it, and then the kernel does magic. And as far as the sender knows, it can carry on doing whatever it wants. That message is somehow moved, as if by magic, into the receiver's address space. Yeah, the sender doesn't care about any of this page management stuff at all. No, the kernel basically manages this all transparently. So the sender, like I said, the sender just has the abstraction that it can send a message. It may write to the memory. It may not. If it later tried to access that memory and the kernel had already migrated the page to the receiver, then the kernel could transparently create a new page there or duplicate the old page there. So basically the kernel is responsible for maintaining an abstraction that the sender is just sending a message. And the message is somehow, as if by magic, duplicated into the receiver. The kernel's responsible for managing all the actual implementation details of that. Okay.
You might be asking, what happens if there's a memory issue?
If there's a memory, well, I'd have to understand what memory issue in the kernel, because if, for example, the receiver's queue is full, if the receiver's queue is full, then the sender's blocked. So the sender's not actually allowed to proceed. So, who is running out of memory in this situation? The whole system. Well, then you have other issues. Yeah. I mean, you have to remember that with all these system calls, and you should be learning this actually on the first assignment, with all these system calls, the system can always say, I can't do it. I don't have enough resources. So you try to create too many processes, the system can say, I can't create any more processes. The system's allowed to do this. So it might be that in that specific situation, Mach would just say, I can't deliver the message. Try again later. And it could certainly do something like that. Obviously, there's a lot of vagaries and nuances to all of this that one could explore. But the main issue here is we're trying to reduce the amount of copying because this is inherently a slow mechanism. It's kind of a really slow mechanism if you look at it. Okay, so another issue, we'll try to speed up here, is that Mach 3 uncovered another issue with microkernels, which is that these components that are managing things don't always have all the information they need to actually solve the problems they're responsible for solving. So the virtual memory pager is a really good example of this, where it's required to make a decision about what page should be evicted across all the processes in the system. But the issue is it doesn't know how other parts of the kernel or other parts of the system actually behave. And so what they found is that Mach did, funny that we're talking about low memory situations, Mach did terribly in low memory situations because it wasn't aware of all the other parts of the system that may have, may be applying memory pressure. It may not know what things have constraints or demands. So again, you could probably design around this issue where the pager starts getting really sophisticated, but then when you have enough information you have to share with the pager, well, then passing those messages is going to become really slow. Monolithic architectures really don't have this problem because all the subsystems can see each other. And subsystems can interact directly with other subsystems very efficiently, so you kind of avoid this kind of issue. So this was one of the big issues that they uncovered with Mach 3.0. Mach 4 tried to fix some of these things. You'll notice the last point here. How did people try to solve the performance issues they ran into on Mach 4? By undoing the microkernelness of the microkernel. We're going to start moving stuff back into the kernel. So we're taking a step back to, sort of the monolithic world. So that's when Jochen Liedtke came into the picture, and it was kind of a really interesting thing. I wish that he'd lived longer. But you kind of unfortunately find that a number of these people that were really impactful on computer science, some of these systems implementation things, typically died, unfortunately, well before their time. He died in a car accident, and I just wish that he had lived longer because we would probably see some really powerful things. But he started looking into microkernels. It became very interesting to him. And he looked at this stuff and he said, part of the problem is just that these microkernels are being designed badly. And so he started designing his own microkernels, which you can see how he named them, L2, L3, L4. He just sort of called them Liedtke's System 2, System 3, and System 4, and so forth. And basically re-implemented the IPC mechanisms from the ground up, and he had them humming along. Order of magnitude performance improvement. First thing, he said, if most of our interactions are synchronous, why actually try to implement them on top of an asynchronous mechanism? Let's provide a specialized synchronous send and then receive operation and actually incorporate that into our process scheduling details and so forth. And so now I trap into the kernel to send, but I also inform the kernel I expect a message back. So I don't need to trap in again to receive. I just trap in once and then I wait. Okay, so now you've already cut that overhead in half. L4 again tries to eliminate a copy during message-based IPC when it has to copy stuff at all. We'll talk about that in a second. So process A invokes the kernel to pass a message to process B. The kernel temporarily maps process B's target memory into process A's address space. So instead of copying it into a kernel queue and then into process B, why not just manage the queue in process B's address space? It's a little bit riskier. You'll notice that this approach to microkernels is a little bit riskier because now process B could really mess up its queue. But if we do this, then we eliminate a copy in the kernel. We can just copy it directly to process B. Also, numerous messages turned out to be really short. If I want to say, yes, the hard disk access succeeded, yes, I created the file for you, why actually copy memory? Why not just pass that stuff in registers? That makes a whole lot more sense. And so short messages are handled differently in the L4 microkernel as opposed to long messages. L4 also schedules a little bit more fast and loose than Mach did, for example, where basically if I have a situation that I do a send and then receive to another process, I am basically telegraphing that I am incapable of proceeding until process B executes. And if I do that and I have like a huge percentage of my time slice left or something like that, why even invoke the scheduler? I know another process that can proceed. Why don't I just switch to it? So in these situations, the scheduler, I shouldn't say the scheduler, I would say the kernel, because it doesn't invoke the scheduler, switches directly to process B and allows it to start executing. Okay? So that removes a huge amount of the overhead. And so there's a number of research papers about this. If you're interested in looking at some of those things and seeing the performance improvement that was able to be achieved over things like Mach with Liedtke's various approaches, it's really remarkable to read about. And it really sort of revamped interest in microkernels. Like I say here, it does affect real-time scheduling. I'm not going to talk about that just for the sake of time, but you can imagine if you're going to stop invoking the scheduler may say, yeah, but so-and-so really needs to run right now, and you're like, I don't care, I'm just going to switch to this other process. Then clearly you start having real-time scheduling guarantees start to be affected. Okay, so this was good for microkernels. It really increased interest in them, but they do reduce reliability to some extent. You can see how we start relaxing the constraints and the boundaries between processes and the boundaries between process data and kernel data for the process. We start introducing a little bit of risks. So there are actually variants of the L4 microkernel approach that are being used in a number of places. So mobile devices, hypervisors are starting to rely on the L4 kernel. You can go look at the Open Kernel Labs website if you want to read more about L4. And they have a surprisingly impressive list of customers that they are working with. And then you also have the open source L4 kernel if you want to go and start working on that, or look at how they do things if you want to emulate it yourself. I think this is very promising, and I think we have not seen the end of it. So it's kind of exciting to see the microkernels live on with some of the obvious brain damage resolved, so that we can actually make them suck a lot less. Okay, any questions? So that's microkernels. Of course, these have performance issues, mainly because of all the IPC overhead that's required. And so hybrid kernels are sort of like microkernels, except that we migrate stuff back into the kernel. Okay, so it's kind of like a blending between microkernels and monolithic kernels. You have a lot more structure in place, because remember, if you try to design things with a microkernel architecture, you are required to think about the interfaces between systems. You can't just throw it all together and patch things wherever you want. So I just want to talk about a few of these things kind of quickly. OS 10 you would call a hybrid kernel because it is based on Mach 3, but a lot of services have been migrated back into the kernel to make it fast. So OS 10's kernel would be an example of a hybrid kernel. Windows NT, which probably nobody uses anymore because we're sort of on to Windows 7 and 8, and there's been a lot of development on those. That would also be a good example of a hybrid kernel. When they started designing NT for the first time, they said, well, Mach is really promising. This was back in the 90s, and so we're going to try to emulate Mach's microkernel architecture. They did it, and it was too slow. Well, how do we solve that? We'll start migrating stuff back into the kernel. And there's a few others as well. The reason, you probably never heard of Chorus OS, but there's a number of research operating systems which are definitely worth checking out if you're curious about this kind of thing. Chorus is really interesting because it basically allowed you to create a microkernel architecture, a microkernel operating system, and then what you could do is declare that certain user space services would be sucked back into the kernel. So they call that co-locating it with the kernel. So we're going to move this thing back out of user space, back into the kernel, and now we're going to actually run it as part of the kernel. So you could the modularity of this was configurable, so that you could actually do this. It is a pretty powerful and interesting approach. So Chorus is definitely one to consider if you're curious about that kind of approach. The last major approach that we're going to talk about today, this basically covers all of the approaches, by the way, which is kind of neat. But, so we say that there's a major difference between monolithic kernels and microkernels. Throw everything in the kitchen sink into the kernel versus pull everything out of the kernel that we possibly can. But it's interesting because that's really only one dimension. They still have a strong similarity in that they both provide this really simple abstraction over the computer hardware. They don't actually allow applications to interact with the hardware directly, like nearly at all. And the file system is a great example of this. We've been talking about it a lot because it's useful for the command shell. But, applications don't care about the file system format or anything like that, or even what type of device. They just interact through this very simple Unix API with the file data. So exokernels are another approach that basically goes in the exact opposite direction away from that. Exokernels explore the question, what if the OS didn't force us into a specific abstraction for interacting with the hardware? Which is kind of an interesting question to ask. This concept was also developed in the mid-90s by the MIT Parallel and Distributed Operating Systems group. And they sort of asked the question, well, who really knows how we need to use the hardware? The answer is the application knows what it's doing and what it wants to do, so why not let the application manage the hardware directly and get the operating system out of the way? Now you might be saying, wow, that seems like a really horrible idea, and certain aspects of it would definitely be a horrible idea. Basically, the OS still retains the power of deciding who gets access to what hardware. So the OS still guards applications from each other, keeping applications from stomping on each other. You can have this part of the disk. I don't care what you do with it. Do whatever you want. You get this other part of the disk. You're not allowed to trample on each other. So things like that might be the way that applications are allowed to access hardware resources in a safe way. Applications can say, I want these ports. I want to interact with these ports. Get out of my way. I want this memory region. Stay out of my way. And then the OS would enforce that. The exokernel, again, the fact that we're giving direct hardware access is, again, orthogonal to whether it's monolithic or a microkernel. Although you can imagine that since exokernels are moving out a lot of things like device drivers and stuff like that, because we're going to let the application do it, they tend to be more in the microkernel vein anyway, because they just don't need to provide very much. But the whole concept of an exokernel is just that I don't control the hardware as much. The application does much more. So how do we actually provide hardware abstractions? They tend to be provided in this approach called a library OS, or a library operating system, which runs on top of the exokernel, but it knows how to talk to hardware. Now the device access is actually in user space. Okay? And so that sits on top of the hardware, and it allows you to have standard APIs provided in a simple way. And then applications can just decide what libOS they want to use. So they don't have to use every library OS. They're not constrained to. If they want to talk directly to hardware, they can. If they want to provide their own libOS, they can. And if they want to use some other libOS that's provided by the system, they can. So they have a lot of flexibility. So MIT, exploring this whole exokernel approach, created XOS, okay, for exokernel operating system. And of course, they created a confusingly named libOS called XOS also on top of XOS. And basically, that provides the standard Unix APIs on top of, in a libOS that applications can choose to use or choose not to use. So that basically, again, allowed them to start running existing applications like Emacs and GCC and other simple applications that are written against the Unix API. So those things could continue to run on top of XOS. But then applications could also ignore that libOS if they wanted to. And so they created this web server called Cheetah, named, because cheetahs are fast. Not because it sounds like cheater. And basically, it had a whole bunch of customized things that it did. Okay, so think about what a web server needs to do. And I need to be able to serve web pages, but web pages access other shared resources. So why don't I create a file system that clumps those things together on the disk so that I don't have to slew the diskette very much? Great idea. I mean, this was fantastic for the 90s. Now we just throw a solid state drive in there, spend a little bit more money, and the problem goes away. But that was the approach back then. They had a custom TCP IP implementation that understood that HTTP was what was being used on top of it, so that they could actually optimize some of the the flows through the protocol. And then when you have TCP retransmits, which you invariably do, well, don't actually use a network buffer where you have to copy data off the disk into the file system cache and then into the network buffer and then out across the network. Why not collapse those buffers? So now TCP retransmits come directly out of the file system cache. That's fast. So they were able to get, again, nearly an order of magnitude improvement over comparable web servers at the time because they were getting so much of the overhead out of the way, which is pretty clever. Okay. Any questions? So that's the idea behind exokernels. What happened to the web server? You could probably still track it down if you looked carefully, but it probably is like boring and slow now because there's been so many, there's some interesting things that we won't talk about for a few more lectures, but things like, I don't know if you've heard of ePoll or Select, but you have various abstractions that are provided on the hardware. I guess what I'm trying to say here is the hardware is making such fast strides and improvements in capabilities. Now we have solid-state drives. We don't care about disk seeks. We don't care where files are. And memory's getting faster, and networking is getting faster, even management of the networking resources and so forth. So that now we can we're getting to the point where we can create modern web servers using more standard approaches that are not nearly as scary as Cheetah would be to manage and maintain, the source code of. And you get really good performance out of it. So it's like these kinds of approaches, while interesting, have kind of remained only in the experimental phase. So you haven't really seen them catch on. But yeah, if you want to look up Cheetah itself, I think you could probably still find it. I don't know that MIT is doing any research right now. What you'll notice a lot of times is that schools will do research in areas because it's interesting to some of the professors or some of the graduate students, and then over time, areas wax and wane. They come and go because people, there's not people interested in studying a particular topic at a particular school. So I don't know the current status of it, but I imagine that it's probably defunct by now. Okay, any other questions? I could be totally wrong about that, of course. So yeah, still open area of research. So you can, I have lots of links in this lecture so that you can go look at stuff. So the Parallel and Distributed Operating Systems Research Lab, you can still look at that. A few other exokernels which you might want to be aware of. Nemesis is a now defunct operating system. And basically it was an effort to try to migrate as much work out of the kernel for multimedia processing and multimedia management, move as much of that effort out of the kernel as possible. So they didn't set out to create an exokernel, but they just ended up creating one because that's what the problem sort of required. Okay? So that would be one to look at. You can see it's an old project that is not really developed anymore. But there's another exokernel, XOMB, which is at least last time, 2 years ago, was still being very actively maintained. So again, if you want to look at an existing active exokernel project, you can look at XOMB. All right, so there's some ones for you to look at. So these are basically the full spectrum of approaches that people have tried with operating systems. You have the simple structure, which is no structure, layered structure, which is a very rigorous you sort of have a subsumption architecture where each layer is covered up by the layers above it, and you have very simple APIs and very heavily tested. monolithic kernels, which are very popular because of their performance, microkernels, which are very popular because they are aesthetically beautiful, but not popular because they're not very fast, and then exokernels, which are out on the periphery, not really very popular just because of how much effort they require. There are variants of these. You might get on the OS Dev Wiki, which is a great website for this class. I probably should collect some links to that kind of thing as well. You'll see nanokernels, picokernels, and it's like, really? They're just mixings of these. Okay? So you take exokernels and throw this away or add that, and you get some other kind of kernel. This basically covers all of the important details. Okay? There's also one thing that's obviously missing, which is hypervisors. Okay? I don't recall if I actually have a hypervisor lecture. I need to write one, but I'm not sure I have space for it. So when I say I didn't mention hypervisors yet, we may not get to them. I hope we do. I don't know. Maybe if we had a special lecture, then you might all come out for that. And because the classes end on a Wednesday, so maybe on a Friday we could do a special hypervisor lecture. Okay, any questions? All right, so we'll pick it all up on Wednesday.